My objective today is to derive the Maxwell-Stefan diffusion formulation, starting with the theory and tenets of irreversible thermodynamics. I also compare the Onsager formulation for multi-component diffusion with the Maxwell-Stefan formulation. Everything I present today is contained in the supplementary information accompanying my paper, Diffusing Uphill with James Clerk Maxwell and Joseph Stefan, published in Chemical Engineering Science 2019. My presentation today is a follow-up of my talk, Irreversible Thermodynamics of Diffusion, on my YouTube channel, and also related to this presentation are two other videos, What Drives Diffusion and Uphill Diffusion, also on my channel. Diffusion in n-component mixtures, the rate of entropy production can be expressed as the sum of the products of two factors. One, a driving force, and the other one, the differences in the velocities of transport of component I with respect to a reference velocity. In this case, the mass average reference velocity for the mixture, V. The second law of thermodynamics asserts that the rate of entropy production must be positive definite. The various terms in this expression are as follows. C sub T is the total molar concentration. R is the gas constant. D sub I is the generalized driving force for component I that I shall discuss shortly. And U sub I is the velocity of transport of species I. The generalized driving force consists of a sum of three separate contributions. The first one is due to the gradients in the isobaric isothermal gradient of the chemical potential. The second term consists of the contribution of the pressure gradient, and this has a term that is the difference in the volume fraction and the mass fraction. Volume fraction phi and the mass fraction omega I. The pressure gradients are effective in producing relative transport of component species I with respect to the mixture, provided there is a difference in the volume fraction and the mass fraction. The last term consists of contributions due to external body forces such as centrifugal forces and electrostatic potential gradients. The term here, F, with a superscript tilde and a subscript I, represents the body force acting per kilogram of species I. The physical significance of this driving force is that if we multiply D sub I by the total molar concentration C sub T by R times T, we have the force acting per unit volume of solution tending to move species I with respect to the mixture, and this term has the units of newtons per cubic meter. The Gibbs-Duhem equation leads to the constraint that the sum of the driving forces dI must be 0. The rate of entropy production is the sum of the products of the driving forces d sub I times the velocity differences. The velocity differences between component I and the mass average reference velocity, if this term is multiplied by the molar concentration of species I, we obtain the molar fluxes. So essentially, the rate of entropy production is the sum of products of fluxes and driving forces. We remind ourselves that the driving force for species I consists of 3 separate terms. The first term is the contribution of the chemical potential gradient. The second term is the contribution of the pressure gradient. And the third term is due to the influence of external body forces such as centrifugal forces and electrostatic potential gradients. In the Onsager formulation, we may express that each driving force is linearly dependent on all the fluxes of the components in the mixture, and define a set of coefficients beta sub ij, and the Onsager reciprocal relations demand that the matrix of elements beta are symmetric. If we further impose the Gibbs-Duhem constraint that the sum of the driving forces is 0, then we must have this constraint on the beta ij coefficients, which leads to the conclusion that the sum over all components I to n of beta ij must be equal to 0. And a consequence of this restraint is that we may replace the reference velocity v here, which is the mass average reference velocity, by any other arbitrarily chosen velocity. The Maxwell-Stefan formulation, we choose the reference velocity to be the velocity of transport of species I. And the Onsager formulation, therefore, is rewritten in the form: a driving force as a linearly dependent function of the velocity difference between species J and species I. Furthermore, we define a set of paired diffusivities d sub ij. D has a line through it, which equals xi times xj, where xi, xj are the mole fractions of components I and j. Ct is the total molar concentration, R is the gas constant, and T is the temperature. The important advantage of redefining the coefficients in this manner is that for an ideal gas mixture, these relations collapse to yield the kinetic gas theory. The pair coefficients dij are independent of the reference velocity frame and also independent of the number of driving forces that are exerting and causing relative motion. In other words, the coefficient Dij is the same whether the chemical potential gradient acts on its own or in the presence of the pressure gradient and external driving forces. This is an important persuasive advantage of the MS formulation over the Onsager formulation. I also stress this in my presentation on uphill diffusion that is viewable on my YouTube channel.